So, yeah, please go ahead.
Shall I start? Good afternoon, everybody. Thanks for the introduction. And this is the talk of my talk in network security distributed estimation for power function wireless sensor network. And these are the outline for the talk: introduction, transformation, sensor and routing, features for the references. Here the introduction, like we consider the problem of joint sensor selection and routing for distributed estimation upon deterministic scalar parameter. Basically, we use estimate and forward approach. That is, each sensor in a network has to measure its own measurement and figures all the measurement it receives from its child sensor. For example, in figure Y1 and Y2 are the child sensor for Y2. Y1 and Y3 are child sensor for Y2, and figures all other measurements in the form of single flow and sent to their parent node, to the path. So this is we call estimate and forward. Later I will discuss it a little more. And this problem, I will so that this is NP hard, and we will also provide a lower bound to compare our optimality of the sensor. Basically, we consider a linear problem, and for the linear problem, blue estimator is blue. That means the best linear unbiased estimator is the best estimator. And based on that, I am going to estimate the figure blue. Here, xk is the estimated version of the parameter x. Actually, I have to explain the equation later. And I am going to focus more on the NC update, mean square error update. So here, basically, leaf node, I mean the sensor node, has to measure its own measurement y1 and from the estimate x1 hat and per variance sigma, and forward to the parent sensor 2. And sensor 2 measures its own measurement y1 and figures its measurement with the measurement it receives from y1. So and forwards in the form of single flow or packet to the parent. So it doesn't have here y2 is not measuring the measurement from y1. So by this way, the measurement has to go to the same node. And we can say in this ellipsoid form, like the error covariance metric that is in the form of covariance ellipsoid is reducing as we are adding more number of information. So this is the main motive of this paper. Basically, the other motivation comes from the routing. Widely known as shortest path tree routing structure is not optimal in the case of distributed estimation. So, for example, in this simple for this simple example, we consider 3 sensors, and S is the single node where estimation has to be computed, and T is the target. So, in this case, if we are taking measurement from all these sensors, all 3 sensors, and using the routing from shortest path tree, that can be obtained from the well-known algorithm, then this should be not the optimal, because while changing this link to this link, it can be improved. I mean, the power budget can be improved, but keeping the same estimation error. So that means there must be some interplay between communication cost and in the link. Communication cost and the distortion that can improve the estimation quality. This is the main aim of this work. So based on that criteria, we define an equivalent of convex optimization problem. That means minimizing distortion subject to a total communication cost given some power budget. Because we are not going to select all the sensors, we are going to select a subset of sensors that generates a non-explanatory T that is a subset of a graph G. Graph G is a subset. Graph G is a sensor that we are going to deploy in the field. And Pmax is a total power budget that is allowed to select a subset. Here is a network model. In our network model, we use the cost function like FC between sensor I and J by proportional to distance between them, and these are the noise power levels, SNR, and fixed bit length. These are constant and completely depending on the distance between the sensors. IEEE. Papa is the exponent that is already experimentally supported. So I use between 2 and 4. And DTS is a threshold distance. That means if the distance between two sensors is greater than DTS, we are not going to communicate with that sensor, neighbor or parent. By that, we reduce the complexity of the algorithm. But we have to ensure that this sensor has to be reached to the other sensor by the network. So that controls by the DTS. So, as I said, we use linear model in the form of yk equal to hk x plus zeta k, where k equal to 1 to n. Capital N is the number of sensors randomly deployed in a square region. Y like in Rn is a scalar observation. X like in R is an unknown deterministic scalar parameter that has to be estimated. Observation of X is distorted by a scalar hk that is proportional to the distance from target to the sensor k. And it is corrupted by Gaussian noise, that is IID, with mean 0 and variance sigma star. So, given the measurement in the form of linear equation, the optimal estimator that can be given by blue is in this form, this estimator, as well as the mean square error, the associated error covariance matrix. In fact, this is not matrix because we are considering scalar, not vector. So, this is the scalar value of the mean square error while considering all the sensors. I mean, diffuse measurement at the same node or hidden node. So, this is the optimization problem. Minimizing distortion subject to a total communication cost. As you minimize this term, distortion subject to a total communication cost equal to P max minus delta. Delta is a power gap, that is the total power allowed minus the total power incurred. Dk is the variable that controls the subset selection. I mean, if dk is 1, that means sensor is picked, k sensor is picked. If dk is 0, that means k sensor is not picked. And dk is less than or equal to dkp, where dkp is the identity of the parent of k sensor. This we have to this set, I mean the set of parent and its set of sensor k and its parent is obtained from the Bellman 4 algorithm. That has to be stored. So this ensures that the routing, since we are going to select only a subset of tree, a subset of sensor, so it ensures that that subset, the generates a tree T, it has to be rooted at the sync node, because we are going to pick the sensor K if its parents is picked. So this forces that subset selection that has to be rooted at the sync node, so that we can get the estimation, total estimation, as well as routing. So this says that fixed tree, because we are fixing the tree in advance using the Bellman 4, and fixed tree, and later also we are going to relax. So we get the name of fixed relaxation based on we discussed. Before that, I would like to provide some proof about the theorem that joint optimization problem of sensor selection and routing for a distributed estimation under total power budget is anti-hard. The proof can be given by polynomial time reduction from the GSP directed Hamiltonian path to a problem. By the following, we consider simple problem like a problem for determining a simple path, directed Hamiltonian path. For example, we choose a graph of n sensor, and since joint selection routing problem is a convex optimization problem and it is already anti-hard, but we are going to prove here by just simplifying to select some path from n to sync. So this will be equivalent to that Hamiltonian path problem. For that, we just map into a network flow problem by minimizing this term together with the cost function. First, let me tell you this term, minimizing this term is equivalent to this term. Definitely, the proof can be seen in the paper. And the minimizing the weighted sum of distortion as well as the cost can be written in this form, where Fi is the network flow from sensor I to j. So Fij could be 0 and 1 if it is integer, because it is integer optimization problem. And Fcdij is the cost function that is proportional to d raised to the power ij alpha. So in this case, we have to minimize the total cost weighted sum with the total distortion, weighted cost with the total cost. Here, omega is the local weighting factor that controls the quality of estimation based on the total power budget. And this term can be transformed into this term with the network flow around this. The proof for this is also given in the paper because of the time that I am not going to discuss here. And replacing this term here, we will get the final objective. Imagine over only Fij, not Vk. So Vk is not here. That means we are not going, since Vk is to select the sensor. So this is not now this is not a sensor selection. So this is only a routing. So this should be only a routing. So that can be transformed. That can be equivalent direct Hamiltonian path problem from N to S. So we transform from our problem when selection to a direct Hamiltonian path from N to S, and sensor N to S. Now you can give a proof that since everybody knows that DSP problem is NP complete, and here we can give a proof by adding extra sensor I. For example, let us consider that adding extra sensor I makes a graph GI instead G was before. So adding extra sensor I can be connected to each sensor by an additional edge. So transforming or finding out a Hamiltonian path from I to S. From I to S, because N to S is already given, Hamiltonian path is given in the graph G, and finding a direct Hamiltonian path from I to S can be done in polynomial time. So, can be done in polynomial time. And we know that the DHP, that is obtained from only N sensor is NP complete. So, IS DHP, that means adding extra sensor, can also be done in polynomial time. And it is, this must be a little more harder than the DHP problem. So, based on that, if we consider the optimization problem, it will be the NP hard problem. So, based on this concept, we propose two algorithms: fixed tree, relaxation based algorithm, and the next iterative distributed algorithm. In the fixed tree, relaxation based, as I said, we are going to relax the variable because, like finding the value of decay, I mean either 0 or 1 is very hard. That I already explained. So what we are going to do here, just to relax this variable, so that we can pick the values of b's between 0 and 1. And then solve the algorithm by the following step. First, find out the shortest path tree based on communication cost and store the identity of sensor K and its parent, because we are going to use Bk less than or equal to Bkp. And then solve the relaxed problem, this one, and obtain the relaxed values of Bk. So here we can obtain the relaxed values of Bk, and we sort this optimal value in descending order, and we pick the first largest case values of Bk, so that it satisfies the total power budget that is allowed, that is provided, that is P max. So for example, out of n sensors, we picked k sensors, first k sensor, definitely k is less than n, and then we remap the first k values to 1. That means the first k values to 1 and the rest n minus k values to 0. By that we pick the k values, and if we pick the routing from the Bellman Ford, we will get a non-spanning tree that is routing at the sensor as sync node, because we already provided that Bk less than or equal to Bkp. And then we will find that the means objective of algorithm, that is optimize distortion error by this expression Lfix. Solution 1 to k equal to 1 to n, but out of n, n minus k's are 0. So definitely this must be greater than or equal to p star. P star is the optimal solution from the main problem that has integer values of the Bk. Now, here I am going to introduce the lower bound, so that we can compare this Lfix with this lower bound. So we choose the minimum spanning tree of a graph. For example, we have a graph of 10 sensors, so we obtain the minimum spanning tree and minimum spanning tree of the graph, and we locate the target and sync node, and we assign the variable for sync node is always equal to 1, because when we sort it, so Vn plus 1 k is already picked, because in when we sort in descending order, it will be the values from 1 to 0, so this will be always picked, because we are going to send all the measurement to the sync node. Now, we solve this algorithm. Here, this term is already in effect, and we are going to pick the measurement all. And we, as I said, sorry, I forgot to say that the sync node is not going to take the measurement. That's why here is n plus 1 is 0. N plus 1 is 0. And then we solve this problem, and we obtain these values dk. For example, big is having this kind of values. Right? I mean, I picked just randomly to demonstrate how we are going to route, how we are going to find the routing of this MST that is routing at the sync node. So, in the flow, just here I consider the cost flow between from sensor I to j by vi. So vi r, and this is the descent, and similarly with the other direction. So here just here just we want to check the direction flow. If Cij is less than Cj, if Cij is less than Cji, then j will be the parent of I. So the difference is only we have to find out bi's. B's, bi or bj. For example, sensor 1 to 2. Sensor 1 to 2. Sensor 2 is having greater than sensor 1. So this will be 1. For example, this will be 1. This will be 2. So 2 will be the parent of 1. In the other case, 2 will be the parent of 1. In the other case, 5 will be the parent of 2. So in this way, we update the set KKP that we already obtained by the, and then by updating this set, we obtain this total cost and the total distortion. That will provide us the lower bound. Now, comes to the second algorithm. This algorithm is actually in the first algorithm we fix the routing structure and optimize the sensor selection. Here we are going to provide a distributor. This is the in fact distributor algorithm where we are going to trade off the distortion with the communication cost with the weighting factor gamma j. So we start from a backbone from target to sync node. That backbone is obtained from the shortest path tree that already I discussed. So just we are going to pick only the path from T to S and we name it backbone, and we store all the sensors in the path, for example A, B, and C, where we make a set J where J is the neighbors of I. And in this case our objective will be because we are going to consider individually locally at each sensor. So for example, sensor A is having this objective, distortion plus cost. The gamma G is a positive space variant that controls the quality of estimation. I will explain later how that controls the quality of estimation. First, we calculate one hop neighbors for each sensor. So among the sensors in backbone, first we have to calculate the one hop neighbor. For example, A is having red colors link is the neighbor for A, green colors link is the neighbor for B, and similarly for C. So first we calculate one hop neighbor for each I, and then find the best one hop neighbor based on this objective. So each sensor in backbone is having a best one hop neighbor, and then later we find out the best one hop neighbor, that must be 1 in this case. So it has to be connected in so backbone has to be updated. Later we come in the next iteration. This is the first iteration. In the every iteration we have to pick one sensor. So in the next iteration, before starting the algorithm, we have to update gamma, where gamma in such a way that we have to check whether the gain in the preceding stage is less than or greater than the present stage. For example, here if the gain Aj is greater than the j previous, that means Aj is proportional to 1, inversely proportional to distance. If it is greater than that, means it is closer to target. Since Aj is inversely proportional to target, so if it is greater than, that means it is closer to target. So we have to give more importance to distortion metric. In that sense, we have to increase the gamma j. we have to decrease the gamma j so that we can give more importance to Lj. Otherwise, we have to decrease. And also, by the following, we have to check backtrack. We have to check backtrack. I mean, whether there is some suitable path that we can switch. That I explained in the motivation that if we switch this link, we can improve power. So this is called backtracking. This is simple, just like logic, checking the continuous code between parents of the selected sensor. So this time the sensor J is selected. So parent of sensor this link and this link. This link is have to be checked among them, and we have to switch from here to here, and also we update our condition code, because in this case total distortion will be the same. We only have to update the total condition code. Now come to the complexity analysis. Since fixed relaxation base is a integer, it is a fixed point integer optimization, and it is well known problem, and it has a order of n cube, and this like the control algorithm, it is having the order of m, where m is the number of edges, n is the number of nodes, and sorting, because finally we are going to sort, and sorting algorithm will take the order of n log n. So in total this will be the order of n cube, and in our iterative distribution algorithm we start from the backbone. That means we have to at this we have to look at that much operation, and then there is the outer loop, and there is the inner loop that selects a subset of sensors that takes k n log n. So in total this will be k n square log n. That means this is comparable to this one, but less than the previous one. As a result, we place 200 sensors randomly in a square field, where computation cost is taken that I will be explained before, with alpha equal to 4, and the measurement gain which equal to 1. So, and we run our simulation for 100 scenarios, and we average the value. Based on that, the data that I explained before is the total power allowed minus the total power budget. We obtain this graph for iterative distributor that is close to the 0. That means we are, in this case, we utilize most of the power compared to the fixed distributor. And this is a simple example when power budget is going to be max equal to 10. In this case, since this is used to do fixed, here this is a bit locally iterative. So in this case, you can see these bigger links are not there because of the local decision. So this helps us to activate some other sensors that improve the quality of estimation. And this is the mean square error comparison versus the total power budget with the lower bound. Black line is the lower bound. This is a fixed. This is a distributed algorithm. This is a fixed. The green line represents solution from an information-driven based algorithm that I referred to in the paper. That is the work already published. That they consider individual optimization. They didn't jointly optimize the routing and distortion. They pick the sensor based on the best information, and they pick the routing structure later. Just select the sensor and then pick the routing. So this was not joined. And this was when we fix the gamma j values much greater than 1 and much less than 1. In both the cases, we have very poor information, poor estimation. So that motivates us to use adaptive optimization here. And this is the gap with the lower bound. This is information driven, fixed relation based, and the iterative. And this is the MSC estimation performance when increasing the number of sensors from 100 to 200 while keeping the previous sensor kept. I mean, increase the density of the sensor with the same region. In this case also, the fixed tree algorithm is worse than the iterative. And this is not worse because we just run for one scenario, not for details. These are references and the questions. Then I will start my second.
Any questions? Any questions for Santosh? Let me ask one. And an expert. Let me check. Okay. So you are saying a query node will give a query, right? But you don't specify what kind of query. Is it general enough? Cover all possible queries? I mean, what kind of query? Okay.
Actually, we are measuring the environment, like for example temperature. So this
Right.
for example temperature. Each sensor has to measure temperature and send to the parent.
Yes.
It's just a scalar measurement.
I mean, for example, average, maximum. Is it the same for your algorithm?
Average?
If we computing average, okay, in one case. In another case, if we are computing the maximum, okay, in your problem, is it the same? Are they the same?
No, it's not same. We are actually we are using the blue estimator to minimize the distortion.
So how do you evaluate the error? For example, in the case of compute the maximum, then you have to compute the error according to the maximum computation, right?
Yes. Actually, this is the mean. Yes, this is the mean. You are taking the summation S in for example, yeah. We are summing the summing and then taking inverse. These are distortion in at sensor K.
So individually, you have one value
yes,
for each node.
Yes.
How do you know this? How do you know this?
Yeah, because we know that the target location. Oh, I forget to say. We know the target location, and because of the distance, we calculate the when this edge that is already known because of the target location. For example, there is a hit sensor here, hit sensor here, hit sensor here. Because of the distance, we can obtain the sense temperature, and we provide the distance, and we can.
Okay, so in your problem, there is one value, okay?
Yes.
So hidden from all the sensors.
Yes.
So every sensor have one measurement.
Yes.
Okay, so your problem is very different from many existing problems being solved.
Some of them, they should try the target location, they just.
Okay, thanks. Please go to your next talk.
This is the next paper entitled Power Weight Joint Selection and Routing for Distributed Estimation of Converse Optimization Approach. More or less the motivation are the same, but here I am going to discuss about this vector parameter, not scalar parameter. So at one set of sensors, at one place we can measure more than one measurement, and there are different algorithms, not the local distributed algorithm. So the same like in the introduction, formation, and then intelligence selection algorithm, and solution there, and sensors. Again, you need, I think I don't need, or okay, let me start. So our problem is to select a subset of sensors and routing structure for distributed estimation for a vector parameter. And we use the estimated forward approach, and this problem is also the same problem, and it's going to be really hard. For example, here in this vector case, this mean square error, this covariance matrix is having the order of m by m. For example, m is the vector number of vectors that we are going to estimate. So this error covariance matrix is having m by m size, and the covariance is equivalent covariance equivalent vector is given by this. So as we take the measurement, as we choose the measurement, the square has to be reduced. That's the so again, I think I can skip this one because I already explained. So here, in this case, we use the linear model, but with vector measurement. So y lies in Rn. So n is the number of sensors. So y is having n measurements, and x is the number of parameters that we are going to estimate, vector parameters. And x is the matrix that contains the other like small h. For example, H is R, N by M. So N sensor is having M measurements. So H 1M, H 2M like this. So in this case, the estimator will be given by the group, will be by this equation, and the error covariance, associated error covariance matrix is given by sigma x. Now considering only the measurement from individual sensor, for example, K sensor, so then it will be a scalar, yk equal to S k transpose x plus zeta k. And then in that case, final error covariance matrix can be given by this matrix, this is by matrix. So based on that, our optimization problem can be minimizing with respect to positive semi-definite matrix Sm. This minimizing the covariance matrix, so the total combination cost again with this constant and the variable 0 and 1 says that it's the optimization problem. And the same proof because the same formulation. Here was interesting point I forget to tell you before that in our this combination, this is now there is no B case, that means there is no sensor selection, it is only routing from sensor N to N, that means this is just equivalent to direct Hamiltonian path problem. But because of this cost, because here is the cost function, if we give less weight omega here, so this could be the negative, so this total could be the negative. So that will, I mean, it will be very hard to solve this problem because this will create a negative cycle in a path. So this will not be a single path. So this material, this shows that this problem will be hard. Now here is the point. Since the problem is an integer optimization problem and minimizing this matrix is very hard when this parameters is on the order of n. So what we did, okay, here is not a guess. This is your here biggest lies in 0 and 1, only 0 and 1. So what we did, we just transform from this vector objective to a scalar objective by some kind of scalarization. For example, we use A optimal formulation because this is the best case in our formulation. But we are going to minimize the error. So error transport, that means trace of error transport is just equivalent to the new square error. So compared to other optimal scalarization, for example, D optimal, we choose D optimal because this is just sitting for new square error. In this case, the objective will be trace of this, that means this scalar value. So now we are going to minimize the scalar of this value. So there is nothing changed, just only from vector to scalar to minimize the complexity of the algorithm. And also realize these values. So the total will be like the same algorithm, fixed selection based, just comparing considering the vector case. So algorithms are same, following the same principle, we obtain lower bound and the same lower bound, but okay, considering MSP and the different objective. And here is the algorithm for improvement from the previous algorithm. So from previous algorithm, what we obtain? I mean, from this algorithm, given a power budget, we obtain K sensors, subset of K sensors. And we start from that subset of K sensors that has a non-instrumentality T. For example, we assume that that subset is having a total commutator called CK. And we generate a subgraph GS out of K sensor, that must be subgraph of G. So we start from the result from the fixed relaxation base, and we improve by using the S-sort method. So S-sort method followed by the local distributed estimation. So first I will explain about the S-sort method, how we are going to swapping the H and we will get the improvement. So in this case, we start initializing the sync node as is S, and n plus 1 is the sync node, but we use total number of sensor n, and n plus 1 is the identity of the sync node. So we assign sync node as S, and k equal to 1 is the number of iterations. I mean, number of k1 is the integer that goes to all the sensors in a subset S. So ns is the nearest sensor where k is the number of. So in the first step, we have to find out the nearest sensor to S. So in this case, for example, this will be the nearest sensor to S. And then we have to check if k is equal to k. That means if we traverse all the sensor or not. In this case, not. So then we have to go to step 6. And if it is yes, then we have to go to step 6 for local distribution. If we traverse all the sensors, but in this case, not. So we have to go to step 3. We have to check if this link is in the tree. That is the non-spanning tree because due to the subset of k sensors. So we have to check whether this link is present on this tree or not, because we are going to swap with the swap the edge between the tree and the link that is not armed in tree, so that we can improve the power. So we first have to check whether this link is in tree or not. So here it is in tree, so we don't have to swap. And then in the next step, we have to assign this sensor to sync, and then we have to find again the nearest sensor to this. For example, this is the nearest sensor to this S. And in this case, this link is not present in T. So what we have to do is we have to find this. Yes. Oh, okay. So we have to find out the most effective link that can be swapped with this. For that, first of all, we have to find out all the links that are lies in T and that are greater than DSM. For example, these green links are the links that are greater than this link, except these two links. And we have to calculate this max of all Dij. Dij that means the links that are in T and that are greater than DSM. For example, this is the link that is greater than this, and it shows that while making this swap, it has to be rooted thing, because we have to also ensure that the update will be looking at the thing. And then we swap with this link. Also, we have to minus this cost because of this link and add this cost. And finally, we will improve the communication cost definitely. And by the following, we get some more swap, and the total communication cost will be the less than what we obtained on the previous algorithm. So we are going to utilize in the next step for that total communication cost to activate some other additional sensors. So we did local distributed optimization, where again, as in the first paper, we make a weighted sum of these two metrics, distortion of an individual sensor plus the communication cost with gamma j. Here this is norm-proof matrix. So there is a proof how to come from m by m matrix to norm-proof, because this is pseudo because m by m that was non-inversible, so it is pseudo-inverse. So we get norm-proof, and we find out the best one of neighbor, just like the previous paper, best one of neighbor, and then find out among the best one. And then we update the tree. That means we create this link, also the subset, that means the x and the cost. And then we update gamma j, and then go back to step 6, following the same procedure, and keeping in mind that the total cost is not exceeding the given power budget. The total cost Ck is not exceeding the given power budget. Once it is integrated, we stop, and we will the total objective and also the guess. In this case, since this is a fixed tree, I already explained this is having the order of empty, and here we are adding additional operation, for example, S sub method plus subset improvement. But these are very less compared to this operation, so the most significant improvement by this more or less both are having the same complexity. And here is the solution result with the same scenario. The lower bound in the local distributor is close to the 0 compared to 60. And these are the performance with the lower bound. L fixed is the fixed based on fixed speed, and L local is based on local distributed optimization, and LP. Here I added another algorithm that is based on linear programming algorithm. That is not they don't use estimating forward. Instead, they use measure and forward. So, a sensor they used to collect all the measurements and then forward to their parent. So there are instead of sending one flow, they send more than one flow. So they incur a lot of cost. So yeah, I just added just to see the comparison. And this is the gaps between this dual model. And this is again the scalarization of sensors from 100 to 400. Keeping the sensor 100 fixed, and adding 10, 10, 10 replacing.
This time, any questions? For Santosh? No. So in the previous paper, the budget is about number of communications, right?
Here also, but there it was just only, I was considering only one measurement.
One measurement. So this time, many measurements.
Yeah, it can be humidity, smoke, heat temperature, heat. So it can be a device that can measure more than one measurement.
Right. So this in this paper, the budget is again power measured in number.
What is the same?
The same.
Yeah.
Okay.
And the algorithm is different. Here we are going to update the subset. We already obtained the subset from the algorithm, fixed from the like centralized, and we improve the subset by swapping, and then we update by local distributed. So in this stage, okay, in my journal, I am going to compare these two, trade-off between these two algorithms because of the phase limitation I couldn't do here. So in my journal, I already submitted, I accepted partially in signal processing. There I presented this two trade-off between these two algorithms.
Okay, good. Thank you. Thank again. So next speaker, Ashraf from University of Vanderbilt. Okay.
Can you hear me? You can?
Can you hear me?
So, the main question we are trying to answer in this work is, if we are given a wide sensor network in a detection application, how can we design the communication network to optimize the detection performance? So essentially, we are not talking here about the signal processing algorithms only, but also we are talking about the network details, physical layer, net layer, and so on. So let's take this small network as an example. Assume we have an area and it's divided into resolution cells, and we have the question of if we want to detect an object at a specific resolution cell, which sensors should participate in the detection process, and what are the communication parameters that should be used? So the answer to this question could be easy if you are talking only about the signal processing aspect of the system. For example, the quality of the information, like signal to noise ratio. We can say, okay, if this is sensor 3, for example, and this is a decision unit, and the resolution cell is located here, then we would say, okay, S3 will participate in the detection process because it's much closer to the target. So its quality of information will be high. However, if we started to include other aspects, communication aspects of the system, the answer may be different. For example, here, this sensor is far from the decision unit. So although the quality of the information is high, the information may be lost in between. So in this case, there is no definite answer. We can just use heuristic ways to answer this question. Which sensor should transfer? the situation also becomes much more complicated if we consider other aspects like, for example, energy reserve. So if we assume, for example, S3 has a high energy reserve, and although the communication channel may be bad, it may use extra power to overcome the channel conflicts. So clearly we need a formal way to answer this question. Which sensors will contribute to the detection process and what are the communication conflicts? So here we formalize the design process, which is a cross-layer because we include different layers of the communication system. So essentially it starts with defining our performance measure. In detection application, usually it's ROC curve or detection coefficient or whatever certain measures. Then after that, we study which quality measures we need to include in our design. In this case, as I explained, we included the quality information, channel state information, and residual energy information. Based on these quality measures, we define the components of the system that we will model to include these quality measures. For example, given these quality measures, we need to model the physical channel, the MAC layer, and the sensor energy, and of course the oscillation model. Now, if we specify the components of the system, then essentially we define our design variables that we need to optimize. Then after that comes the system model, which essentially gathers everything together. It expresses our objective function, our performance measure, in terms of the design variables and the quality measures. And then after that, we carry out the optimization. We solve the transition problem and we compare our results. So this is essentially the outline of the talk. I will go quickly through this process. So in this work, we consider three levels. And let me explain here, there are two phases in this problem. The first phase is carrying out the optimization algorithm to specify which sensors will contribute and what are the communication parameters. This is usually done at the beginning by the decision unit asking sensors to transmit their parameters about a specific resolution cell. Then this information is propagated back either at the decision unit or at parent nodes. The optimization problem is solved, and then the design variables are propagated back to the sensor nodes. Now, every sensor knows for each resolution cell is going to contribute to the detection process or not, and what are the communication parameters that it will use. Now, this solution will become valid until there is something changing in the network. After that comes the detection process. In this case, the decision unit broadcasts a message saying that, okay, I want to detect if there is something at a specific resolution cell. Sensors receive this message and check their tables if they have to contribute to the detection, in this case, the detection task or not. And then they carry, if they will contribute, they will sense the environment, propagate back the information to the decision unit for a final decision after a specific period of time. Now, this information could be quantized or unquantized. We consider both cases. Now, some assumptions here. The first one is the tree is predefined, so I did not consider the routing problem in this case. And the other one is nodes who are sharing one parent, they do not interfere with each other, different parents. So for example, this set of sensors do not interfere with the other set of sensors. This could be done in practice by different frequency ranges or using smaller power, not to interfere with the other sensors. Okay, now I'll go through the design process quickly. So the first thing is in our detection problem, we have well-known performance measures like the ROC curve, suppressing the probability of detection versus the probability of false alarm or probability of error. The problem with these measures is it's very hard in this case to use them to get tractable results because I'm considering different layers of the system, so the situation becomes very complicated when optimizing with respect to these measures. Fortunately, there are soft measures like the detection coefficient, which does give tractable results in this case. And the good news is the detection coefficient is directly proportional to these other measures. So the higher the detection coefficient the better the detection. So this is essentially our objective function. This is what we are trying to model in our system, to express it in terms of the network parameters. Now after that we need a statistical model. So in this world, we assumed amplitude measurement from the sensors. And the observations are given by this expression here. This is a mean value of the signal and amplitude of the signal. So this signal could be either reflected at the target if you are talking about active sensing, or it could be just emitted from the target if you are talking about passive sensing. This is the mean, this is the added noise, and given this observation model, we can get this expression for our detection coefficient. This is our objective function. And the variables into our design variables. So this is our representative communication rate, where the sensor communicates back to the parent node its observations. Now if we look here, we will find that in the expression, well, the expression looks complicated, but it's not actually very hard to see that it is simply the signal to noise ratio of each sensor, but they multiplied by lambda, which is a probability that the information will be successfully transmitted to the decision unit. Now, to calculate this lambda, we need to start modeling the physical and math layers of the system. So moving on to the wireless channel to model the physical layer. In this case, I assume large scale grading, which means that there is a minimal movement, so sensors essentially are fixed with respect to each other. And added gas and noise, given these two assumptions, we get this channel capacity expression. Now, omega, of course, is the bandwidth for the channel. PR is the power C. Now, given the state-of-the-art decoding schemes, we can abstract the channel model as on-off model, which means that if the communication rate we are using is less than the channel capacity, then the channel will be on and the information will be received. If the communication rate exceeds the channel capacity, then the packet will be lost and we can consider the channel as off. Now the question here, so why don't we use always communication rate less than the channel capacity? Well, the problem is the channel capacity is not fixed because the power loss in the channel is probabilistic. So what happens is the channel capacity is moving depending on the channel state. And it may happen that the capacity may be less than the communication rate we are using, but the channel will be off. So the question is, how can we model the power loss in the channel? So we use this well-known path loss model, which essentially is a magnitude plus a white noise. And given this expression, finally we can find an expression of what is the probability that the channel will be on at any given slot of time. Now this probability is expressed in terms of, again, our design variables, transmission power and communication. Now this is not the whole story. If I can remind you here, we are talking about two layers here, the physical layer and the math layer. The channel will be on, may be on, but at the same time, if we move to the math layer, there may be collisions between sensors. So even if the channel is on, the information may be lost. So we need to move on again and model the next layer. Now here I assume a simple version of a solid aloha where the detection cycle is divided into slots. And to simplify the analysis, I assume that sensors are synchronized and that the number of slots at each level of the tree is an integer multiple of the number of slots at the subsequent layers of the tree. Now, the decision center waits until here and then takes a decision. Now, at each time slot, each sensor attempts transmission with probability QI. This is one of the design variables. So it's not hard to show that, of course, here we have to be careful that the communication rate at each node has to support not only its observations, but as well the information coming from child nodes. So, skipping all these details, we can show that this is a probability of no collision between sensors when transmitting, and combining this math with the physical layer model, we can reach this expression for the probability of successful transmission of the packet. This part is for the MAC layer, this part is for the physical channel. Now, if you still remember this line that appeared in the expression of the deflection coefficient. So now we have a complete description of our objective function. We are seeking to maximize this value with respect to our design variables. The only thing remaining is the transmission power. Now, for this, we need the energy model. So in this work, in other words, for single mode, we consider the energy allocation problem, or to simplify the analysis. We assume that pre-allocation for the energy by sensors for each deflection cycle based on a fixed lifetime for each sensor. So essentially, we fix the lifetime for each sensor, and based on the initial energy in the battery for each sensor, it allocates the energy to each deflection cycle. This, at the end, this gives us this expression, which essentially eliminates one of the design variables in terms of the other one. Again, PT is transmission power for the sensor. Q is attempt probability in the MAC layer level. Now, putting all these things together, we got our optimization problem here. Here we have this is our objective function expressing the deflection coefficient, our detection performance, in terms of the communication rate for the sensors, and the attempt probability on the MAC level. And of course, these are our constraints. So unfortunately, this optimization problem gets more and more complicated with the tree size, and it will not be practical just to solve this global optimization problem in practice. So clearly, we need a more practical approach. If we look carefully here, we will see that this expression reflects the tree structure. We can see this by this expression. We can express our optimization problem in a recursive way this way. So this shows us that we can solve smaller local optimization problems starting from the leaf nodes and then going up in the hierarchy of the tree. After solving each local optimization problem, we go up and solve another optimization problem and so on until we reach the decision making. This has an advantage that the local optimization problems will be solved locally, so we don't need to propagate all the information back to the decision unit. And also, it's much more practical. Now, this is a local optimization problem. It is not convex, and it's very hard actually to prove any convexity properties even in the subdomain of the function. But the good news is the constraints are linear, so the Larouche-Pontefract conditions are necessary, which means that we can use existing gradient-based algorithms to solve it. However, we can't guarantee global maximum because the algorithm may describe a local maximum. So this is a numerical example for our network composed of eight nodes of the decision unit. And we modeled this system and compared it to other approaches, best approaches for the design implementation. The first approach is the decoupled, where we do not integrate any layer. For the physical layer, for example, we say, okay, we will put a communication rate to guarantee a minimum success rate for let's say 40% or 90% of the time we and we calculate the communication. For the MAC layer, usually it's designed to guarantee fairness of sensors. The other approach is maximum throughput approach, where we maximize the average communication rate. This design scheme, integrates the physical and MAC layers. Our scheme is different that it integrates the three layers. So it's different from this one, and it takes into account also the quality of the information of the sensor. So it's not just maximizing the quantity of the information, it maximizes the quality of the information. So this is the result here. This curve shows, this is the detection coefficient, our performance measure against the delay for detection, the detection cycle length. This one shows the solution of the global optimization problem. This one shows the local solution that we proposed. And this one is the max throughput design, and this is a decoupled design. Clearly, our approach outperforms these two classical approaches. However, this is the loss in performance due to the local optimization algorithm. Of course, this loss of performance, I mean, we can draw general conclusions here because it essentially depends on the network setup and performance. But in general, always this approach will be outperforming the other approaches because it takes into account, as I said, the quality of the information. Now, what I have said, we perform this design based on, we take the sample observations and we just transmit them without any quantization. We compare this approach to this case where we quantize the information. So when we get the observation at each sensor, we use only a few number of bits to quantize the information and send it to the decision unit. Well, there is a trade-off here. If we quantize this observation, then we lose some information. However, using less number of bits, this means that the communication rate could be lower, and then the probability that the information will be received at the decision unit will be higher. So there is a trade-off to the question, which one will be better? Well, the answer is, it depends on the delay for detection. So comparing the direct transmission approach with the e-network processing, we find that there is a breakpoint here for the delay threshold. Before that, the direct transmission approach outperforms. After that, the situation reverses. So the main idea here is, in this case, the delay for detection is small. So for the e-network processing, we lose information by quantizing, and we don't have enough time to compensate for it. Also, we have enough energy so that we can overcome the channel losses in case of the direct transmission, because we are using the higher communication rate. Essentially, this situation is reversible. So we call this region where the signal processing aspect of the system is dominating. Here, the communication aspect is dominating. This breakpoint depends on many things like the network architecture and mainly the quantizer design. So coming to the conclusion, the cross-layer design is, of course, it results in enhanced performance. But the problem is it is much more difficult to carry on in practice by hand. We have done this by hand. In practice, we are not expecting design engineers to do this by hand because it's very hard, especially if you are going to go through the design process several times. So I guess software tools to automate the design process would be essential. Local approaches, of course, even if we lose some performance, it's still much more practical. The future work, as you see, there are some design assumptions that need to be relaxed. Like, for example, one of the comments I got from the people is noted a local protocol. It's not very practical, not used anymore. I mean, CSM, ACD, or C are used extensively, but that would make the analysis much harder. Another thing is energy allocation. I use the fixed energy allocation scheme here. This is one possible extension. And the routing problem, of course, I assume that the tree is already formed. Therefore, I eliminated the network layer for your design. This is also one more essential possible. So, any questions?
Any questions? No? Let me ask one. Okay. So you assume sensors share different parents. They don't have interference, right? If you do consider the interference, what would happen to your algorithm?
What will happen is, well, the design process is the same, but the problem is this expression will be much harder, because essentially this expression is saying that it's taking into account the information coming from here only through one route, from here to this one to this one. And it considers only the collisions between this sensor and these sensors. So the only thing that will happen is that when you consider interference from here, you will start considering collisions from other sensors as well. So the concept is the same, the expression will be much harder, the transition
I see.
will be
Good. Good. Excellent work. Thank you. Thank you. Because we are running behind the time schedule, so let's skip the break. Okay? Because there's anyway no coffee over there, so let's continue. Okay? Next paper, resource allocation with stochastic demands. Okay? The authors cannot come to present the paper, but they do have a very good friend, Joseph from City University of New York. Okay, so thank you. Please go ahead.
Thank you. So the paper is resource allocation with stochastic demands. It's a joint work of the Penn State University and the University of California, Los Angeles. The first author is a PhD student, and he's advisor Thomas Laporta, and Maggie Sirvasalis from the UCLA. So the problem is the resource allocation. And the problem is defined as follows. Well, we have a network applications are supported by a variety of resources. For example, the resources in the end devices can be CPU, memory, disk. In network, it can be a bandwidth and spectrum. And the resource requirements in all dimensions need to be satisfied. And one system can meet a subset of applications at the same time. So the goal is to maximize the total profit admitted to the system without exceeding the resource limitations. So if the demands are deterministic, the problem can be formulated as a multidimensional knapsack problem. So the PI can be thought as a knapsack size in multi-dimension that corresponds to the facts of the resource I. The AIJ can be thought as items of size or weight, which corresponds to the demands of application J resource I. And CJ can correspond to the eigenvalue, which is the problem of the application profit. So we formulate the problem as a multi-dimensional offset problem where we want to maximize the total profit subject to the capacity constraints in all dimensions. However, the demands are not deterministic, they are stochastic, so in practice the demands for resource may change over time, and only the stochastic or distributions are known in advance. So the constraints of the following form enforce capacity at all time will lead to low utilization of resources. And to overcome this, you want to allow a predefined overflow probability P. So you will replace the capacity constraints with the probability, when the probability should not exceed the given P in all dimensions. There is a lot of related work in this topic, and this problem is in the form of the chance constraint program. And the chance constraint program may be solved by either scenario approximation or a sample average approximation. And in general, it's a hard problem. In fact, for some distributions, such as a Bernoulli distribution, it's even hard to compute the probability such as this. And so there is a need for an efficient solution for this particular chance constraint problem. So they developed the heuristics for the problem, and they compare it with the solution to the chance constraint program. So they use the sample average approximation as an upper bound, and they compare their solutions to the upper bound. So the upper bound is based on the sample average approximation. So what you do, you sample a random variable aij n times and obtain n samples for each aij. And then you generate one big problem instance with all these samples. And the problem becomes deterministic and it provides the upper bound. But it actually explodes the number of variables and it explodes the number of constraints. So to solve it is going to be slow. So how many samples do you want to generate for the problem? For the one-dimensional case, to obtain an upper bound with a specified confidence of 1 minus delta and gamma, you need to satisfy the following condition. And the result actually can be extended from the one-dimensional case to a multi-dimensional case in a straightforward manner. So they provide the heuristics that will solve the problem faster, and the proposed solution for our framework is as follows. You let the beta px denote the effective bandwidth of the random variable or vector with specified overflow probability, and given the effective bandwidth, you can convert the problem, which is stochastic, to a deterministic, and then you solve the deterministic multidimensional set problem. If the effective bandwidth converts a random variable to a random vector to a deterministic vector, you will use the solution, the solver for the multidimensional case, and if it converts to a scalar, you can use the dynamic program for the one-dimensional case. So the effective bandwidth for general distribution can map a random variable to a just a vector, a random vector just to a vector, where its vector is three-dimensional, by using the equation 7 and the equation 8. Or you can also map a random vector to a scalar using the equation 9 and the equation 10. Now you also have the effective bandwidth for some known distributions for Poisson trials only. Since the Poisson variables have the following property that Poisson events with the parameter lambda plus Poisson events the parameter lambda is equivalent to the Poisson event with the parameter lambda 1 plus lambda 2. You can convert the condition of the 3 that this condition, the constraint, to the following inequality. And the G function is the inverse Poisson CDF. So the effective bandwidth for the Bernoulli chain is only available. There is the proposed, and the Klegger proposed an effective bandwidth for the Bernoulli trial of type QS as a following formula equation, where the trials obtained values S with probability Q and Z with probability 1 minus Q. However, this leads to a more constrained problem. So if for the multidimensional subproblem, in general, solving a multidimensional subproblem is a hard problem. So they use a heuristic for that as well, and And for simplicity, they use a modified adaptive fixing heuristic that was introduced by Sigma's engineer. And the algorithm works as follows. They solve the linear program relaxation first and update the optimal solution to the linear program. The x a vector for the linear program, and then they fix the xj element to 0 if the xj element is between the 0 and a predefined gamma, which is usually set to 0.2, and they fix the xj to 1 if the xj element in the vector is 1. And they iteratively solve the linear program relaxation with more and more variables fixed until all variables are equal to 0 and 1. And in case no variables are changing in an iteration, and there are some variables satisfying the condition for x is between gamma and 1, they set the minimum to 0. So to evaluate the algorithm, they generate 5 to 10 resources. And the capacity of each resource is randomly drawn from the interval uniformly for an interval from 2 to 10. And the parameters for the AIJ are drawn randomly. We generate 300 problem instances randomly from each series of experiments. And the combination of effective bandwidths and upside solvers are tested. The following are tested: the D2D, the lambda base, the Bernoulli, and they use the mean as the effective bandwidths. And they pair it with either the multi-dimensional offset or the one-dimensional offset, depending on whether they convert the vector to a vector or vector to a scalar. So this is just the one set of experiment. So in the picture you have the total profit versus the total profit and the full probability. On the x-axis you have the number of problem instances generated, and on the y-axis you have the competitive ratio. The competitive ratio is compared to the upper bound, which is the solution of the SAA, the sample average approximation. So they compare the D2D, D2-1, the mean, and the lambda based, and they see that the lambda based achieve the near optimal solution, where their solution divided by upper bound gives the ratio of 1. And the next, in the comparison, you see that the D2D gives a slightly lower performance. The mean is used as the base to compare with their algorithms. So for the on the second picture, you see the overflow probability, and you see that the lambda based is a very aggressive algorithm. It produces a lot of overflow. The P is set to 50%, so it actually has some instances where it actually produces the overflow 50% for the lambda base. For the D2D is less conservative. It's more conservative than the lambda base. slide shows the experiment where the EP is set to 10%. And here the lambda base still achieves the near optimal solutions, as seen from the first picture, where the ratio is close to 1. And all the effective bandwidths allocated to a more conservative demo, which the D2D is still the most aggressive after the lambda base. For the next experiment, they generate the 9 resources in this experiment, and the demands in the first 3 dimensions follow the Poisson distribution. The dimension of the next 3 follow the Bernoulli distribution, and the dimension of the next 3 follow the exponential trials. And they use the lambda base for the Poisson, and either the D2D or D2-1 effective bandwidth for Bernoulli and exponential, and the total profit of the algorithm compared to the upper bound is shown in the first picture, and the overflow probability is shown in the second picture. In conclusion, in this paper, we decided the problem of allocating multiple resources among a group of users to act with stochastic demands, and we model it as a stochastic multi-dimensional knapsack problem. We used the combination of effective bandwidth and the knapsack solvers to solve the problem, and via numerical experiments, they found the effective bandwidth for general random trials consistent with the satisfactory results. So the next slide shows just the references of the paper, and that's.
Any questions? I think if you have a question, just send email to the others. Okay. Thank you. Let's move to the next paper. Proactive vehicle rerouting strategies for congestion avoidance. The presenter is Miss Panchen. Okay. So I think you are the last one. In the orders for the last paper here? No. So you will be the last one. Go ahead.
Hi everyone. Today, my talk is about how to use proactive strategies to avoid congestion. Traffic congestion is an ever-increasing problem. It causes economical and environmental problems and causes frustration for the drivers. So there are several ways we can do to reduce the congestion. We can increase the road capacity. Some people propose to optimize the traffic signal control. Or alternatively, we can provide better traffic guidance for the drivers, which is the focus of my presentation today. So it has been demonstrated by a lot of researchers that smartphones and roadside sensors can monitor traffic at a very fine granularity. As you can see in this picture, traffic management service can collect data and estimate congestion in real time. They report traffic data to the center. So our idea is the TMS can provide real-time and proactively individually tailored routing guidance to drivers to prevent congestions. So the drivers provide their original and destination information and their route information. The guidance is computed in the server and recommended and pushed to the driver's smartphones when signs of congestion are observed on their current routes. The drivers may or may not follow the guidance. So the main focus of our research is, as you can see in this picture, first, signs of congestion is observed in these road segments. And then the service will automatically select those vehicles who will pass this congested road in the future and compute alternative routes for those vehicles to avoid these congested segments. There's a difference between our work with the existing work. For example, Google and Microsoft, they have real-time traffic information to compute traffic-aware shortest routes. First of all, their solution is reactive. It's like an information board. And second of all, they provide the same guidance for all drivers. So it will cause a problem. Suppose there's one congestion on this road segment. If everyone follows the same guidance, then the congestion may possibly switch from one spot to another. Another related work will be is from the transportation research. So they use mathematical model to model the model is called dynamic traffic assignment. So what they did is they iteratively calculate the shortest paths and assign the routes to each driver to achieve the user or system equilibrium. But there's a big problem with this mathematical optimization because it is very hard. It requires very huge computation time, and it's very hard to provide real-time guidance proactively at large scale. And other problem includes the ability to work when not all the drivers are part of the system, and the robustness to the drivers who ignore the guidance. So our research is trying to elevate the problem and include and provide insights for a real-time deployable system. So my previous slides, I mentioned our motivation and related work. In the following slides, I will talk about our 3 proactive rerouting strategies, associated simulation result, and conclusion to the work. So our rerouting has 4 phases. The road network is represented as a graph. With the estimated travel time as edge weight. So the travel time is estimated based on Green-Shields model. So the input is the density of the road segments. The output is estimated travel time. And then the signs of congestion is obtained when the density is greater than a certain threshold, for example 0.7 in our case. And then the service will select the candidate vehicles and compute the alternative routes and assign to the drivers. So these slides demonstrate the selection of the candidate vehicles for rerouting. Suppose the signs of congestion is observed, and then the system will recursively select the incoming segments to the congested segments until depth L. Suppose L is 2. So first you select the first level of incoming segments, and then select second level of incoming segments, and all the vehicles on those 2 segments will be selected for rerouting. And our 3 routing strategies is as follows. First one is very simple, just the actual shortest path. So it's, as we discussed before, it may have the potential to switch congestion from one spot to another. Another strategy is to compute k shortest paths. And then the system compute randomly similar k shortest paths with similar travel times. And then the system will randomly pick one and recommend this to the driver. The third strategy is entropy-based k shortest paths, which is proposed by in our paper. First, is the same. We calculate the k shortest paths for all the drivers, and then instead of randomly pick one, we pick the one with the path with the least popularity. So the idea is, suppose there are several paths in front of the drivers, so we pick the one which will be occupied the least in the future. So this way, it will reduce the possibility of creating another congestion. So in order to calculate the popularity of the path, we use the entropy information theory. So we know all the routes of all route information of all the vehicles. So we know exactly how many vehicles will pass this road sequence in the next time window. And use that information, we can calculate, we can use this formula to calculate the popularity of the paths. Let me give a brief, simple example. Suppose this is a road network, and then vehicle 1 is assigned a path as this, and vehicle 2 is assigned a path as this one. Vehicle 3 is assigned path CK and HK. So for vehicle 4, there are 3 paths he can take. They are all quite similar and with the same travel time. So which path this one should take? What we do is we calculate the entropy for each of the paths. And as you can see, the path 3 has the least entropy, so we pick this path and recommend it to this driver. Our evaluation is performed on 2 networks. And we use a simulator called, it's an open source simulator called Sumo, based on car following models. And then we use this Python library to send command to Sumo to assign a new path. So our goal is to evaluate the average travel time, the number of rerouting, the average travel, and also want to evaluate the driver's compliance rate and system penetration rate, and also the CPU time. The pattern of the traffic flow generated is as shown in these two graphs. The traffic flow is in 1 hour. For Brooklyn network is 1,000 vehicles. For the Newark is 908 vehicles in 1 hour. So this, as we can see, for average travel time, all the strategies improve the average travel time insignificantly. In particular, the EBKSP, which is entropy-based strategy, has the best performance. Compared to no rerouting, it reduced to up to 80% and 104% in to both of the 2 networks. Compared to the basic dynamic shortest paths, it is better by 15%, 25%. And in terms of the average number of rerouting, we can see because the EBKSP has better carefully and intelligently select the paths for the drivers, so it actually reduced the number of rerouting. So which means it creates less distraction for the drivers. In terms of the average travel time, in terms of the compliance rate and penetration rates, it's intuitively, if everyone follow our recommendation, then the average travel time will reduce. And then when the compliance rate even is quite low, as we can see, compared to no rerouting, the EBKSP is still better, and EBKSP is still the best. So performance increases with compliance rate up to a point. Low compliance rate still much better than no rerouting. So in terms of penetration rate means how many people installed our system. If no one installed, if very few people installed our system, and then the density of the road cannot estimate it accurately, and we cannot detect the congested segment. As you can see, when 40% of people have the system, then all the strategies start taking effect. And when 60% up to 60%, and then the EBKSP start to show the benefit. However, if we can have the help from the roadside sensors, because roadside sensors can help us to detect the density. We can see all the strategies, even under low penetration rate, still much better than the no rerouting. And the EBKSP is still the best. So the performance increases with penetration rate, and with roadside sensors help to detect vehicle density, low penetration rate, still much better than no rerouting. In terms of the CPU time, because as we can see, the Astra, this one is the shortest complexity for the Astra, and this one is the complexity for the K-shortest path, worst case scenario. So very obviously, DSP should consume much less CPU time than the other two strategies. However, when we see the RKSP and EBKSP, we see EBKSP actually is lower than the RKSP. The reason is because the EBKSP reduce the necessity of rerouting. It actually reduced the